In this video, we're going to look at one of the most important steps in neurodevelopment, generating all of the glial and nerve cells that will make up the mammalian brain. Let me remind you that neurodevelopment is a multi-step process. Prior to the events that I'll be talking about in this video, the body would have already set aside the cells that will become the nervous system and set up the chemical cues that will regionalize the brain. And following completion of the events that will be the focus of this video, there'll be still more to do, such as differentiation and growing out axons and forming functional synaptic contacts. So what we're looking at then is a relatively early stage. Let me set the stage by recapping the key events that have happened thus far. Brain development begins with neurulation. This is the process where a subset of cells in the ectoderm separate and form a long, hollow tube. Here I'm showing you the front portion of a human embryo 25 days after fertilization, and we can see the developing nervous system and how it's relatively tube-like, although we can already see a little bit of specialization in the different parts of the developing brain. Although the neural tube is curved in the embryo, neurobiologists typically simplify it by drawing it as a straight structure, and that's what I've shown above. Here we have the three-vesicle stage, and we can see the slight swellings which will give rise to the forebrain, prosencephalon, midbrain, mesencephalon, and the hindbrain, the rhombencephalon. And as development continues, the brain will expand. The tube gets longer and it increases in diameter, and it shows a greater amount of regionalization, so that now we have what's called the five-vesicle stage, where the front part of the brain is separated to form a distinct telencephalon, which will give rise to the cerebrum, diencephalon, that'll give rise to the hypothalamus and thalamus. The mesencephalon will still be the midbrain, and the hindbrain is beginning to show the specializations that will give rise to the metencephalon, the cerebellum and the pons, and the myelencephalon, the medulla. The brown part in these figures corresponds to what will become the spinal cord. Now you can imagine that this kind of growth would involve the addition of cells, and it does. At the very earliest stages, the neural tube consists of about 1,000 cells, so by the three-vesicle stage, this has increased some, although it's still less than 10,000 cells, and by the end of the 7th week, we have something like 100,000 cells in the developing nervous system. I'm going to show you a video to give you a better sense for what these structures look like in the developing embryo. I'll play it through once. And now I'll play it again, trying to pause it. And I've paused it here so you can appreciate the two enlargements that will become the cerebral hemispheres. And if I let it rotate a little more, we can see the bump that would develop into the hindbrain. Now, pictures like this can be a little bit misleading, and I want to show you what I mean. Here I'm switching to an ultrasound. These come from the Global Women's Medicine Atlas, and we're looking at now an ultrasound of a living embryo, a living human embryo. The uterine wall is on the right, just to orient you. Here is our cartoon version of the developing embryo, and I'll go ahead and I'll outline the developing central nervous system in this ultrasound. I'll take this marking away, and now what I want to do is show you some planes of sections. If we take a section through the hindbrain and what's roughly a coronal axis, we will get an image that looks like this. So I hope you can see the midline, the head's up at the top, you can see the two upper limb buds that are developing, and here we can see something about the rhombencephalon. Although it's a large structure, it is dominated by that fluid-filled space. There are very few cells that are making up the wall of the brain. We'll see a similar sort of thing if we take a rough horizontal section through the embryo. Very few cells, lots of fluid-filled space. And finally, here's one more section, and again you can see the mesencephalon, the rhombencephalon, but it's dominated by that fluid-filled space. Now this will not always be true. Here are pictures that are taken from a mid-gestational scan. These are routinely done about 20 weeks of gestation, so 18 weeks following fertilization. I'm going to draw your attention to the section marked D, which is going to be a coronal section towards the back of the brain through the occipital lobe and the developing cerebellum. That's what's shown in the bottom right-hand corner. And here I've added a highlight to show you the hemisphere. And now I'll color in the occipital horn, that back part of the lateral ventricle. And what I hope you can see is that now the ratio of brain tissue to cerebrospinal fluid's really shifted. We have quite a bit thicker cerebrum here, as indicated by the red arrow. What's happened is that there's been a whole bunch of cells that have been made, and those have added to the thickness of the brain. So now that you get a sense for the steps that are happening between the formation of the neural tube and mid-gestation, let's go see how these cells are added. What I'm going to do here is I'm going to return to the early stage embryo. This is that 3-vesicle stage, and we're just going to zoom in at a little portion of the neural tube wall. It looks something like this. Down on the bottom is the lumen, or the ventricle surface. This is what's going to contain the cerebral spinal fluid ultimately. And we have the outer or pial surface, which will face away the outer surface of the brain. And at this stage, when the neural tube is formed, there's really only one type of cell, and it's a single cell layer thick. These are called neuroepithelial cells, or neural stem cells. These are the cells that are going to give rise to all of the neurons in the brain, the 2 major classes of glia, oligodendrocytes and astrocytes, as well as the ependymal cells that will line the cerebrospinal filled cavities. Let me go ahead and draw what one of these neuroepithelial cells looks like. Here it is. These neuroepithelial stem cells show a very specific pattern of cell division. It's called interkinetic nuclear migration. The neural stem cells span the width of the neural tube, and there are special cell-cell and cell ECM contacts that connect the apical surface to the lumen and then the basal surface of the cell to extracellular matrix components. The nucleus, however, is free to move, and it does this during cell division. And what happens is that when one of these stem cells is going to divide, the nucleus migrates up towards the surface, and as it's doing this, it replicates the DNA. The nucleus then migrates back down, upon which it will undergo mitosis and will get cell cleavage. And I want you to notice that I've drawn the cleavage plane here vertically. The cell is going to divide, giving rise to 2 progeny cells, each of which will still contact both the outer and the inner surface of the neural tube. These are symmetric cell divisions. Both of the progeny cells that are generated are themselves neural stem cells. And this type of symmetric cell division is what's dominating between that 3-vesicle stage and the 5-vesicle stage, as the neural tube isn't getting any thicker, but it's increasing in diameter and length. Okay. Now, as development continues, sometime around week 7 in humans, we start to see another type of division. And what happens here is the neuroepithelial cells still go through this interkinetic nuclear migration where they migrate up, replicate their DNA, and then that returns back to the surface. But now when they undergo mitosis, the cleavage plane forms in the horizontal axis. And when these cells divide, we get one neuroepithelial cell, but the other daughter cell looks different. It has no contact with the luminal surface anymore. And this daughter cell then wraps itself around the process for the neuroepithelial cell, crawls up it till it gets to the surface where it will crawl off, and these cells will eventually differentiate to become the very earliest neurons in the brain. Once the neuroepithelial cells begin to divide asymmetrically, the brain will start to get a little bit thicker. We're going to start to see a layered structure in the brain where there'll be a layer of developing neurons. This very outer layer is called the marginal zone, and lying underneath it, closer to the ventricle, will be the radial glial cells in what we're going to term the ventricular zone. Although the radial glial cells share many of the same properties of the neuroepithelial cells, they get a distinct name because they also begin to express different markers. The radial glial cells quickly begin to show a slightly different pattern of division. They still have the nuclear migration where the nucleus moves up and then comes back down, although it no longer reaches all the way to the pial surface. And we still have an asymmetric division yielding another radial glial cell and a progeny cell. But these progeny cells get a different name. They're called basal progenitor cells, and they're also known as intermediate progenitor cells. What these basal progenitor cells is they divide once, or in some species twice, and then the two progeny cells wrap themselves. They're closely associated with the radioglial cell, and they crawl along it until they find a spot, hop off, and then differentiate to become neurons. The presence of these basal progenitor cells then lets us identify a new zone in the developing brain. We still have the ventricular zone, we'll still have the marginal zone up at the top, but now there's a subventricular zone, which at this stage is populated by these basal progenitor cells. The process continues. Another asymmetric round of divisions will yield another basal progenitor cells. And now here I'm going to switch the color of the progeny cells to a different color to make an important point. The cells that are born later, these purple cells, have to migrate past the older teal-colored cells before they can hop off and differentiate to become neurons. Thus, in this picture here, the blue neuroblasts had to crawl past both the teal cells and the purple cells before they could find a layer to hop off and differentiate into neurons. In other words, we say that the brain is developing in an inside-out fashion, where earlier born neurons lie deeper in the brain than more peripheral ones. The only exception are those very early neurons that are born and remain in the marginal zone. At this point, it may be useful to refer to two more zones. The cortical plate refers to the portion of the brain which is populated by all of the newly generated cells, the ones that are going to differentiate and become neurons. Lying underneath it, there'll be an intermediate zone, and this is comprised of white matter tracts. The developing neurons will begin to extend axons into nerve bundles. What I've told you thus far about the radioglial cells and the basal progenitor cells is how the mammalian brain generates the deeper layers of the cortex, everything below the granule cell layer. But late in development, there's another switch. An asymmetric division will lead to the production of two different types of radioglial cells, so that now we have what are called the outer radioglial cells, shown here in a tan, that span through the subventricular zone up to the pial surface, but no longer reach all the way down to the ventricle. These outer radioglial cells divide much in the same way that the original radioglial cells did. Each time they divide, they will self-renew, so that a division regenerates the outer radioglial cell and also produces another type of cell called a transient amplifying cell that again will divide once or twice in order to give rise to immature cells that will then again migrate along the outer radioglial cells and find their home. The development of these outer radioglial cells and the divisions are of great interest to neuroscientists because most of the neurons in the more superficial layers of the cortex are derived from outer radioglial cells. And you might remember that the neurons that are found in layers 2 and 3 of the cerebral cortex are the ones that are making cortico-cortical connections. So these will be the neurons that are allowing different parts of the cortex to talk to one another. And these are some of the circuits that we think are going to mediate the higher cognitive functions that we see in animals like humans. All right, I have just a couple more things to tell you. You might have noticed that so far I have said nothing about the origin of glial cells, but they are also derived from these neuroepithelial cells and the radioglial cells. As development continues, some of the outer radioglial cells are thought to differentiate and become astrocytes. Others will differentiate to give rise to oligodendrocytes, and still others, mostly those that are deeper, still in the ventricle zone, can differentiate to become the ependymal cells. As I've walked you through this process, I've been focusing on how the developing brain is going to generate the bulk of the cells in the cerebral cortex. There are slight variations on these processes that occur in different parts of the brain, so that cell differentiation in the developing hippocampus or spinal cord or cerebellum are a little bit different. But if you understand the process for the cerebral cortex, you'll have a good foundation to understand how other brain areas are generated. One of the problems with focusing on the cerebral cortex is that this is a part of the brain where there are relatively few inhibitory neurons, and it turns out that what I've told you so far refers to how we generate the excitatory neurons that make up 80 to 90% of the neurons in the cerebral cortex. The inhibitory neurons have a different origin. Here we're looking at half a frontal section through a human brain at 15 weeks post-conception. Up at the top you can see the developing cortex with the ventricular zone, the cortical plate, and at the very top the marginal zone. Lying deeper in the brain we have some deep structures, including what appears dark purple there, the eminence. And this can be divided into the medial ganglionic eminence, which is closer to the midline, and then the lateral ganglionic eminence. And what the stars are representing here is the origin of glial cells. Here's another picture illustrating their origin. There are stem cells lining the ventricle, but in the medial and the lateral ganglionic eminences. There are radioglial cells that are dividing and generating neural progenitor cells, much like we saw in the cortex. But the cells that are born there have to migrate tangentially. They migrate along either the outer surface of the brain or along the ventricular zone until they can move into the developing cortex. There they intercalate amongst the excitatory neurons that are being produced, and these will yield the inhibitory neurons, the GABAergic neurons that we see in the adult brain. Cell proliferation and migration is an active area of research. There are a lot of people that are trying to understand the genesis of the cells that make up different parts of the brain to see how they are different from one another, as well as to look at the cues that are involved in migration. I think, however, we'll stop the video here.